All right, hi everybody. My name is Alex. I am the U.S. Direct Sales Manager and Lab Manager for Shodex. Thank you for joining us today for our webinar, The Basics of Size Exclusion Chromatography, uh, with Dr. Tanya Napolitano. She's our Technical Manager for the U.S. We hope everybody's in the right place. We're excited to talk chromatography with you. Let's get started. Tanya, if you could take it away.
Thank you, Alex. Okay. Hello and welcome all to the first Shodex webinar. Once again, my name is Tanya Napolitano. I'm the Technical and Marketing Manager at Shodex. And today I'm going to be talking about the basics of size exclusion chromatography. So during this presentation, I'll touch on the following points. First, I'll introduce Shodex and tell you a little bit about who we are. Next, I'll talk about size exclusion chromatography principles to achieve pure SEC. And then I'll go through solvent, pore size, and silica versus polymer selections of different columns. And then we'll talk about method development, considerations, do a quick summary, and then I'll let you all know the best way to contact us. So first, who or what is Shodex? Shodex is a brand of LC columns that have been manufactured by Showa Denko in Japan since 1973. Now we're under Resonac America Inc., and our columns are designed to provide superior separation and purification of complex mixtures. Shodex is known as a specialty brand due to our polymer packing, and we have over 1,000 different columns covering the separation modes listed here to match the various separation needs of different industries. A little more about Shodex branded LC columns starts with our core technology. So Shodex core technology starts with gel particles that fill the inside of the column. Depending on the type of chromatography, we use different monomers, such as styrene, vinyl alcohol. Then using our synthesis technology, parameters such as particle size, pore size, and pore volumes can be controlled to produce reproductive columns. And lastly, we can add on different functional groups for surface modifications for targeted separation of various analytes. And these three varying parameters create the different modes of separation that are in our broad product portfolio, which includes helic, ion exchange, saccharide and organic acid analysis, SEC columns, ion chromatography, LCMS, chiral columns, and special application columns. Okay, so now that you know us a little better, let's discuss some size exclusion chromatography principles. I'll just use SEC for short. So the basic principle of SEC is based on separating by hydrodynamic radius. So shown in this green graphic, we have three different molecules, and even though they might have different molecular weights, these samples are taking up the same space. So for example, these three analytes have different molecular weights, but they're taking up the same hydrodynamic radius based on how the analytes are folded in 3D. So during separation, let's look at this pink Pac-Man, and this is going to refer to the gel pores packed in our size exclusion chromatography columns. So analytes with high hydrodynamic radius and or high molecular weight, such as this orange ball, are too large to go through the gel pores since it's larger than the maximum pore size, and therefore it will elute first. Then the maximum pore size shown in the purple will elute next, and following the trend, the minimum pore size will elute last. So in principle, large molecules elute faster in size exclusion chromatography, or SEC. So many people want to use SEC to determine molecular weight. However, one needs to make sure there's no interactions between the stationary phase and the analytes for pure size exclusion chromatography, or pure SEC. So different known molecular weight standards are used to generate calibration curves based on their retention time. And you should choose the standard with the most similar structure and behavior to your sample that is available when generating these calibration curves. Then you can inject your unknown sample and estimate the molecular weight based on the retention time in the calibration curve. So you may have heard terms before when you were looking at size exclusion chromatography, such as size exclusion, gel permeation, gel filtration, but they all operate under the same principle. So pure SEC is based on the hydrodynamic radius. Therefore, we want to minimize other interactions such as hydrophobic or ionic partitioning between the stationary phase and the analytes. And this will determine accurate molecular weights. So in this presentation, we're going to go through the major considerations to achieve nearly pure SEC for a variety of proteins and polymers. Two useful definitions to start with are the exclusion limit and the permeation limit. So the exclusion limit shown in green is the upper limit of the molecular weight or molecular size that can be separated. And the permeation limit is the lower limit of molecular size or molecular weight that can be separated. So the first important consideration of starting an SEC method is understanding the solubility of your sample. Once you understand what kind of solvents or buffers your sample can be dissolved in, you can start picking a mobile phase and a column that can handle that specific solubility. So this is a graphic summary of all the Shodex SEC columns that we have available and their compatible solvents. So we see with gel filtration chromatography, or GFC, columns compatible with hydrophilic solvents are to your left. And then we see gel permeation chromatography, or GPC, columns compatible with organic solvents to your right. And I'll come back to GFC and GPC specifications in the next slide. However, I'd like to quickly point out that we have silica or polymer-based columns in this graphic, and I'll also describe that in a later slide. So first with GPC, gel permeation chromatography, here we see an overview of our original Shodex SEC columns that we produced in-house 50 years ago for our own polymer analysis to analyze our own specialty non-polar polymers. Specifically, GPC is gel permeation chromatography used for non-polar solvent SEC. The terminology is not extremely important, but for non-polar polymers, this is a handy guide for column selection based on the solvent solubility of your sample. For example, if your sample dissolves in DMF, you'd look into these column series, or THF, you'd look into these column series. Okay, next we have for the analysis of aqueous and or polar polymers such as proteins, peptides, nucleic acids, or various other polar polymers like polyacrylamide. This has traditionally been referred to as GFC, or gel filtration chromatography. So this is a useful slide if your compound is water soluble. We'll go into more in depth on the differences in using a silica-based GFC column, such as the KW series, or a polymer-based GFC column, such as the SB series, later in the presentation. So if your sample is water soluble, this is a handy guide to start with the column selection. So next, you want to pick a suitable standard for your method. And this is very important for molecular weight determination, as well as monitoring the health of your column. So these are some examples of common SEC standards based on their eluent solubility. So we highly recommend picking a standard that has similar properties to your sample. For example, if you're analyzing starches, Polulin, which dissolves in water or buffer, is probably the best standard because it's a linear straight chain sugar, and so that's great for starch analysis because it behaves similarly to your compound. Okay. Next, after picking a column series based on the solubility of your sample, the next important factor in SEC column selection is the pore size. So pore size is important if you think back to the exclusion limit and the permeation limit. So if you pick a column with a pore size that's too big or too small, then you won't achieve pure SEC for the molecular weight distribution of your sample. So the correct pore size will allow for a symmetrical Gaussian bell-shaped curve for the total molecular weight distribution. So in this example, the sample analyzed was polyacrylamide polymer with an average molecular weight of 5.5 million Daltons, and the sample was tested on 2 different columns, same series. So SB806 and SB807. SB806 has a smaller pore size, and SB807 has a larger pore size. So with the smaller pore size, you can see that in this blue curve, the peak is not symmetric. And you might see this peak and think there's significant tailing. However, the shape is caused by missing the higher molecular weights of the samples. So that was excluded from this part of the curve. But when you use the SB807, which has a larger pore size for this molecular weight sample, the full molecular weight distribution is accounted for due to the larger pore size. And you see the pink curve is nice symmetrical bell-shaped curve. So for this case, the SB807 shows correct molecular weight distribution. Next is the silica versus polymer. So this is specific for GFC because we have packing that is either silica or polymer, but for our GPC, it's all polymer based. So specifically focusing on GFC or aqueous SEC, there's another useful distinction, which is silica versus polymer. So proteins typically have a narrow molecular weight distribution. So you want a more defined pore size to give you high resolution and sharp peaks. So silica-based columns such as the KW series is more suitable for the analysis of proteins because the distribution of the pore size of the silica-packed column is comparatively narrow compared to the polymer-based columns such as the GF or the SB series. You see there's better separation with this KW studying these proteins. So polymers, however, have a wide molecular weight distribution. So you'd want to pick a polymer-based column such as the SB series in comparison to the KW, which is silica, because the distribution of the pore size of the SB polymer column is comparatively wider than the silica-based columns. Okay, in general, if you target your sample, if your target sample is in a smaller molecular weight range that is covered by one pore size, then you'd use a single pore column, like the KF804. So this graphic is describing the pore shapes. So, but if your target sample has a wide range of molecular weights that isn't covered by one pore size, for example, here we have a couple samples that are ranging from 500 kilodaltons to 100 daltons. So with this wide range, and it's not covered by one pore size column, Shodex offers columns with mixed and or linear pore size base columns. So these columns are packed with different pore sizes to account for a larger range of molecular weights. So For example, the chromatogram shown in the mixed pore of the KF804L gives you a wider molecular weight range. You see there's more resolution for peak number 7 in comparison to the KF804. So we're happy to discuss the specifics of using either single pore columns or using mixed pore columns for your separation after the webinar, because it could get a little complicated based on the specifics of your analysis. Next, another useful tip to improving SEC performance is to use multiple columns in series to improve the resolution. So in this example, we see one LF404 column can separate these polystyrene standards. However, when a second or third column is added, the resolution and the chromatography improves because the surface area of the stationary phase has increased. The two things to note is the runtime does increase, and second, it's important to pick the correct column to add in series depending on your type of analysis. So now once you have a column picked, you're ready to optimize a method. So in this example, povidone was analyzed. It's a linear polymer. It's suitable in both water and it's soluble in both water and acetonitrile. However, based on the first runs, we noticed hydrophobic interactions and kinks caused by the 100% water conditions. So we were able to reduce these hydrophobic interactions with the packing phase by adding more hydrophobic solvent gradually. So in this case, with 40% acetonitrile, we see less kinks, less disturbances, and a better chromatography. So you want to make sure you're reducing any hydrophobic or occasionally hydrophilic interactions by modifying the polarity of the mobile phase. So this is one of the most common method optimization parameters that you'll see in SEC. Another extremely common method optimization is dealing with ionic interactions with the solid support. So this is especially true for proteins or polymers with ionic functional groups such as polyalylamine analysis. So here we see at low buffer concentration in red, the polyalylamine interacts with the solid support and it has delayed retentions, which generates incorrect molecular weight data. So you can see that by the 0.2 molar sodium nitrate red curve. By adding a suitable amount of sodium nitrate, which is around 0.2 molar of salt, this is going to prevent the ionic interactions between the analyte and the solid support, which generates the correct molecular weight distribution data shown by the green curve. So this is also very common in method optimization, either modifying the salt content or the hydrophobic content. So to conclude the SEC basics, we first need to know the solubility of the sample, which can help us determine the column series to pick. Next, based on the molecular weight distribution, we pick the correct pore size and distribution, silica versus polymer. Then you want to pick standards to help your analysis. And lastly, optimize the method to reduce any interactions between the stationary phase and the analytes. So the easiest way to find any of our resources is to access our website, shodexhplc.com. You can type in your sample name into the search bar and find applications relevant to your analysis. You can also download our catalog, column manuals, C of A's, technical articles, posters, and different publications. And pricing and credit card ordering is available for US users. Lastly, please contact us at support@shodexhplc.com. Our team is based in New York City. We have a lab with a trial and demo program, so we can help you develop a method or run your samples for you. as well as give columns or trial programs to help you find the right analysis conditions. We do direct site visits. We love to hop on quick Zoom or Teams calls to discuss any technical support. So please contact us for any additional information.
Thank you for your time. If there's any questions, please let us know.
Thank you, Tanya. Thank you very much for that overview. We have 2 questions. So yeah, Tanya, go ahead.
So one question's, do you have any applications for PEG molecular weight 3,350? What do you recommend? So PEG or polyethylene glycol is soluble in water or buffers. So using that information, we can go to the catalog. Hold on really quick. I need to share my screen. So polyethylene glycol is a polymer. So I'm going to the polymer section. Here we go. So for polymers, you can go, you can find this in our catalog. So it's water soluble polymers. So that should be the SB or the LB series. And then with that specific molecular weight, you can see the different, one second.
If you go to page 40, Tanya.
Yeah.
So yeah. 40 on the page. Yeah, 42 on the PDF. Sorry.
Okay. So for SB, okay. So 3,000, around 3,000 Daltons I would recommend the SB 802.5 to cover that molecular weight range. And also the SB is compatible with water. Is there any other questions?
Yeah, we have a second. If you have a 500 kilodalton protein, what column would you recommend?
For proteins, you can use the KW series.
So it's just up. Yeah.
So KW series is the silica-based columns, and that's better for proteins. And then with that molecular weight range, I would recommend
So yeah, you're kind of right at the edge between a 404 would probably be better,
yeah,
or a 403. Yeah. Yeah, so you're probably safer with a KW 404 or a 804, and that'll cover your range for that large proteins. Okay, cool. I don't see any other questions right now. Okay, yeah. But we are happy to answer any questions offline. Please email us. And thank you very much for joining us today. We're going to wrap up here, unless anybody has any last minute things. And yeah, thank you very much for joining us, and have a good day.
Thank you.